So I have the vector A, B. We're starting at A, and notice we're heading towards B. In column form, it is 3, 5. We're going to look at that and compare it with the vector P, M, starting at P and ending at M. Notice as a column vector, it is also 3, 5. What do you notice about the vector AB and PM? They're the same. So AB is equal to PM, and this is what we describe them as: equal vectors. Equal vectors have the same direction and the same magnitude. Now let's look at the vector VR. Starting at V, traveling up towards R, and as a column vector it is 5, 2. We're going to look at that and compare with the vector SW, starting at S and ending at W. Look at the values. What do you notice between them? One is the opposite of the other. One is a positive 5 and a positive 2, and the other is a negative 5 and a negative 2. This is what we describe them as. One being the opposite vector. Opposite vectors have opposite direction but the same magnitude. So we could say that SW is the negative of VR, or SW is the opposite of VR. We could also look at it at a different way. When we have RV, if we wanted the RV, we had to do the opposite. We have to travel against the vector VR. So when you're traveling against a vector, you use the negative, right? So if we wanted RV instead of VR, we could use the negative of VR. And look at what happens to that. See? Now we're starting at R and we're ending at V. So we need to do the opposite, which is the negative of 5, 2. And then we're going to distribute that negative sign on the inside. A 5 gets the negative and the 2 gets the negative. Let's look at WS. So we're starting at W this time and we're ending at S. It is the opposite or the negative of SW. So see, it's starting at W now and going towards S, the opposite or the reverse. So to do that, we need to use the negative of the vector SW. So we're going to have to distribute that negative to the negative 5 and that negative to the negative 2. So negative and negative will give us a positive. So it now becomes a positive 5 and a positive 2. Look at the vector FD. It is 1, negative 4. And let's look at the vector KC. It is 2, negative 8. What relationship do you think exists between them? Look at the size of FD compared to the size of KC. And look at the numbers. You could say that KC is 2 times FD, or FD is a half of KC. This is what we call parallel vectors. Parallel vectors have the same direction but different magnitudes. Or you could express it as one vector is a multiple or a factor of the other vector. Look at the vector px. Starting at p, traveling upwards to x. It's 2, 4. And now we have another vector, xb. Starting at x and going up to b. It is 1, 2. What do you notice about both of them? Well, they form a straight line and they share a common point, x. Something else is interesting about them. Let's see if you found it out. So if you notice, xp would be 2 times xv, right? Or you could say xv is a half of px. And notice too that they share the common point x. This is what we call collinear vectors. They're parallel vectors that share a common point. They form a straight line. One more thing. Let's look at position vectors. Position vectors start at the origin. I would normally call the origin O, and the coordinate for O, the origin is 0 on the x and 0 on the y. So it can be written as a coordinate, and that's a position vector, right? And your x value comes first, and then your y value comes second. So let's look at the vector OK. K is at the point 4, 3. And if we're going to write OK as a vector, we would use its coordinate 4, 3. We could write it as a column vector as seen, or we could write it as a coordinate. What about OH? Starting at O and going to H. The coordinate of H is negative 1, 2. And notice, because it's a position vector, it starts with O, and we just write it as its coordinate. You could write it as a column vector, or you could write it as a row vector, or as a coordinate. Negative 1, then 2.